A warm welcome to all of you in the second part of the chapter Principle of Effective Stress. Darcy, a French engineer, in 1856 derived an empirical formula for the behavior of flow through saturated soil. He found that the flow through soil occurring per unit time is directly proportional to the head causing flow and the area of cross section of the soil sample, but is inversely proportional to the length of the soil sample. That is, Q is directly proportional to del H by L into A. After removing the proportionality sign, we get Q is equal to K into del H by L into A, where del H by L is the hydraulic gradient. Then we can write the equation Q is equal to KIA, where Q is the flow in unit time, K is the hydraulic coefficient of the soil or coefficient of permeability, A is the cross-sectional area of the soil sample. Now we can write discharge per unit cross-section area as discharge velocity, that is Q by A is equal to V. Then Darcy law may be expressed as V is equal to Ki. The actual velocity of water through the void spaces, that is seepage velocity, is greater than the discharge velocity. A relationship between the discharge velocity and the seepage velocity can be expressed as V is equal to N into Vs, where N is the porosity of soil and Vs is the seepage velocity. Since the Darcy law is based primarily on Darcy observation, so there are some limitations of this law. This law is only valid for sands, silts, and clays, and this law is not applicable for gravel and other coarse material. For validation of this law, soil should be completely saturated and flow should be laminar and one-dimensional. Due to presence of continuous voids, every material is permeable in nature. The permeability of a soil is a property which describes the ease with which water flow through that soil. The unit of permeability is length per unit time and is expressed in centimeter per second or meter per second in SI units and in feet per minute or feet per day in English units. The coefficient of permeability depends primarily on the average size of the pores, which in turn is related to the distribution of particle sizes, particle shape, and soil structure. In general, the smaller the particles, the smaller is the average size of the pores, and the lower is the coefficient of permeability. The hydraulic conductivity of soil is inversely proportional to the viscosity of water, which decreases with increasing the temperature. For a given soil, the coefficient of permeability is also a function of degree of saturation. The hydraulic conductivity of unsaturated soil is lower and increases rapidly with the degree of saturation. The same soil may exhibit different degree of perviousness depending on its structure, that is void ratio. A loose soil is much more pervious than when it is dense. Even while all soils are permeable, the degree of perviousness is different. Gravels are more permeable than sands, sands are more pervious than silts, and silts are more pervious than clay. Some typical value of hydraulic conductivity for saturated soil are given in this table. Casagrande and Fadum have also gave permeability range for different types of soil, which is shown in this table. The knowledge of the permeability is essential in the solution of many engineering problems involving flow of water through soil, such as dewatering and drainage of excavations, backfills, and subgrades, determining yield of water-bearing strata, determination of seepage through the body of earth dams, and computing the losses from canals. The coefficient of permeability can be determined in three ways: by laboratory test, by field test, and by empirical approach. The Standard laboratory tests are used to determine the hydraulic conductivity of soil, the constant head permeability test and the falling head permeability test. IS 2720 Part 17 deals with the method for the laboratory determination of the coefficient of permeability of soils. The coefficient of permeability for coarse soil can be determined by means of the constant head permeability test. A typical arrangement of the constant head permeability test is shown in figure. The soil specimen at the appropriate density is contained in a perspex cylinder of cross-sectional area A. The specimen rests on a coarse filter. A steady vertical flow of water under a constant total head is maintained through the soil and the volume of water flowing per unit time is measured. The total volume of water collected may be expressed as Q is equal to area into velocity into time. As per Darcy law, we can write velocity V is equal to Ki. Then Q becomes A into K into I into T. After putting the value of I as H by L, we get permeability K is equal to QL by AHT, where Q is the volume of water collected, A is the area of cross section of the soil specimen, V is the discharge velocity, T is the duration of water collection, K is the hydraulic conductivity or coefficient of permeability, I is the hydraulic gradient, small h is the head, and capital L is the distance between manometer tapping points. For fine soils, the falling head test should be used. In the case of fine soils, undisturbed specimens are normally tested and the containing cylinder in the test may be sampling tube itself. A typical arrangement of the falling head permeability test is shown in figure. The length of the specimen is L and the cross-sectional area A. A coarse filter is placed at each end of the specimen and a standpipe of internal area A is connected to the top of the cylinder. The water drains into a reservoir of constant level. The standpipe is filled with water and a measurement is made of the time T1 for the water levels to fall from H0 to H1. At any intermediate time T, the water level in the standpipe is given by H and its rate of change by dH by dt. The rate of flow of water Q through the specimen at any time T can be given by minus A into dH by dt. Negative sign indicates that head is decreasing with time. As per Darcy law, Q is equal to K into I into A. Substituting Q with minus A into dH by dt and hydraulic gradient I with H by L. Further simplifying the equation, we get permeability Q is equal to 2.3 into small a into L divided by capital A into T1 into log H0 by H1. The reliability of laboratory methods depends on the extent to which the test specimens are representative of the soil mass as a whole. More reliable results can generally be obtained by in situ methods. In the field, the average hydraulic conductivity of a soil deposit in the direction of flow can be determined by performing pumping test from wells. The figure shows a case where the permeable layer whose hydraulic conductivity has to be determined is unconfined and underlain by an impermeable layer, and the test well extends to the bottom of the permeable stratum and is perforated over the section which is below the water table. In its original state, it is assumed that the groundwater is at rest. During the test, water is pumped out at a constant rate from a test well that has a perforated casing. Several observation wells at various radial distance are made around the test wells. Continuous observations of the water level in the test well and in the observation wells are made after the start of pumping until a steady state is reached. The steady state is established when the water level in the test and observation wells becomes constant. The pumping generates a radial flow of water towards the test well, and as a result, the water table assumed a curved surface called drawdown water table. Consider the flow through an elementary cylinder of soil having at radial distance r, thickness dr, and height h. The area of the vertical cylinder surface through which water flow A is equal to 2 pi rh. Analysis is based on the assumptions that the hydraulic gradient at any distance r from the center of the well is constant with depth and is equal to the slope of the water table, that is I is equal to dh by dr, where h is the height of the water table at radius r. This is known as the Depute's assumption. As per Darcy law, the rate of inflow into the well when the water levels in the well remains stationary, that is Q is equal to KIA. Substituting for A and I, the rate of inflow across the cylinder surface is Q is equal to K into dH by dr into 2 pi Rh. After rearranging and integrating, we get permeability K is equal to 2.3 into Q by pi into log 10 R2 by R1 divided by H2 square minus H1 square. A confined flow condition occurs when the aquifer is confined both above and below by impermeable strata. The average hydraulic conductivity for a confined aquifer can also be determined in same manner as earlier case. Consider the flow after a steady state is obtained. From Darcy law we can write Q is equal to KIA. For a confined stratum of thickness h, the area through which seepage takes place is A is equal to 2 pi Rh, where R is variable and H is constant. Then we can write Q is equal to K into dH by dr into 2 pi Rh. After rearranging and integrating, we get K is equal to 2.3 into Q by 2 pi H into log 10 R2 by R1 divided by H2 minus H1. There are also some empirical approach to determine coefficient of permeability. One form of equation that gives fairly good results in estimating the hydraulic conductivity of sandy soils is based on the Kozeny-Kármán equation. According to Kozeny-Kármán equation, permeability K is equal to 1 by K naught into S square into gamma by mu into EQ by 1 plus E, where E is the void ratio, gamma is the unit weight of liquid, mu is the viscosity of that liquid, S is the specific surface area, and K naught is the factor depending on pore shape. Extensive investigation of filter sands by Hazen laid an equation for hydraulic conductivity, which is K is equal to 100 D10 square, where D10 is the effective size and K is in centimeter per second. One more equation in terms of permeability is log Ks square is equal to A plus Bn, where N is the porosity and A, B are the constants. Hydraulic conductivity can also be found if the value of coefficient of consolidation and volume compressibility is known. That is K is equal to Cv into Mv into gamma W, where Cv is the coefficient of consolidation, Mv is the coefficient of volume compressibility. This equation is suitable for very fine grained soil such as homogeneous clays. In a stratified soil deposit where the hydraulic conductivity for flow in a given direction change from layer to layer, an equivalent hydraulic conductivity can be computed to simplify calculations. For horizontal flow that is parallel to bedding planes, the hydraulic conductivity is written as summation of Kh divided by summation of H, that is K1 H1 plus K2 H2 plus K3 H3 divided by H1 plus H2 plus H3 And for vertical flow, equivalent hydraulic conductivity can be written as summation of H divided by summation of H by K, that is H1 plus H2 plus H3 divided by H1 by K1 plus H2 by H2 K2 plus H3 by K3. The continuous void spaces in soil can behave as bundles of capillary tubes of variable cross section. Because of surface tension force, water may rise above the phreatic surface. The upper surface of the zone of full saturation of the soil is called the water table or phreatic surface. At the water table, the groundwater is subjected to atmospheric pressure, and the pore water pressure at this ground table is zero. Every soil in the field is completely saturated up to some height above the water table and partially up to some more height. This is attributed to the phenomena of capillary in soil. Capillary water is held above the water table by surface tension. We can get an understanding of capillary in soil by idealizing the continuous void spaces as capillary tubes. As shown in figure, consider a single idealized tube. At equilibrium, the downward forces equal to the upward forces. Here, the downward forces are weight of column of water of height hc, and the upward forces is the vertical component of the surface tension force around the circumference. After equating these, the forces in the upward and downward direction, we get capillary rise hc is equal to 4t cos alpha divided by gamma w into d. For chemically clean glass and pure water, alpha is equal to 0. Then capillary rise Hc becomes 4T by gamma W into D. After putting the value of surface tension T and unit weight of water, we get Hc is equal to 0.03 divided by D. From this equation, it can be seen that the column of water is greater when the diameter of the tube is smaller. One approximately recursive suggested by Terzaghi and Peck is Hc is equal to C by E into D10, where E is the void ratio, D10 is the effective grain size, and C is the empirical constant. Height of capillary rise for different types of soil is given in this table. The effective stress principle is probably the most important concept in geotechnical engineering. The compressibility and shearing resistance of a soil depend to a greater extent on the effective stress. Thus, the concept of effective stress is significant in solving geotechnical engineering problems such as the lateral earth pressure on retaining structures, the load bearing capacity and settlement of foundation, and the stability of earth slopes. Thank you.